So in the previous screencast, we talked about the history of glass. And so now we're really going to dig around into what is glass. So glass is made of silica. And silica is just a way of, or a word for SiO2. So Si is silicon, and then we have two oxygen atoms, and that whole unit is called silica. And other stuff. Okay, and we're going to talk about what that other stuff is in a little bit, but it would be like sodium silicate or calcium silicate. But there are other things mixed in. When we talk about glass, glass is a solid that sometimes behaves as a liquid at room temperature when it should normally be a solid. Okay. And so it's characterized as a supercooled liquid or an amorphous solid. And so, of course, the question here is why? Why does it do this? Well, basically, it's a non-crystalline solid. What that means is it has a definite shape and volume. But if a glass sheet remains in place over a long period of time, that glass will flow. And that's why old windows appear really wavy. So I have a picture up here of old windows that eventually appear wavy. Is that glass is not rigid, it will move at a really, really slow speed. Now, the reason it does that is because glass has a different atomic structure than a typical solid. Now, glass is not a crystal, right? It's an amorphous solid. And so crystals themselves are true solids. And so I want us to talk about crystals for just a moment. Glass is not a crystal. There are 4 categories of crystals. We have ionic and organics, and these are held together by strong electrostatic forces, right? An example would be sodium chloride, which I have a picture of right here. Other examples would be things like calcium carbonate. Okay, those are all ionic and organics. Then we can have metallic crystals. These are metal atoms that are arranged in a crystalline array. An example of this would be iron or aluminum or copper. And so I have an example of iron here. Then the third category are molecular crystals. These are covalent molecules. Such as iodine or iodine chloride. They are characterized by being really soft. They have really low melting points. And are insoluble in water. So, for example, this is a molecular crystal there. And then the last category of crystals are network solids. These are covalently bound. In I don't want to say in, I want to say to form. To form one large network. Okay. They are insoluble in water. And examples are things like diamond, which I have a picture of there, graphite, and quartz. Now, quartz is pure silica, SiO2. It's nothing else is mixed in. And so I want us to contrast quartz, which is a crystalline solid, with glass, which is an amorphous solid. So I want us to dig around into that just a little more. So quartz, I said, is a crystalline solid. It is SiO2, which is called silica. These are examples of quartz, and they are very, very ordered. This is pure silica. There is nothing else in there. So all the atoms are arranged in a regular repeating pattern called a crystal lattice. And this is formed by the slow cooling of that melted silica. So I want you to pay really close attention to how ordered this is and how it's just SiO2. Now let's compare that with glass. Glass is an amorphous solid. Silica is the basic ingredient of glass. But its crystalline order has been disrupted due to rapid cooling of melted silica. So one of the things that I want to point out here is that one of the differences in how this is formed is glass is formed when you have a rapid cooling of melted silica. Quartz is formed, if you go back to the previous slide, with the slow cooling of melted silica. Now, so that's one of the ways that we have this contrast of how they're different. Another thing to be aware of is that glass contains other substances that affect the properties. Right? And so those include oxides, and we're going to talk about some different oxides and how they affect the properties in just a second. So this includes oxides. I want to point out this picture right here, and I want you to compare it with the previous picture. The previous picture showed very organized quartz. This is fused silica glass, and I want you to notice it's just a random arrangement of atoms. That's it. It's all random. It's all over the place. So we've got kind of three kind of big ways that silica is different. One is it's formed by the rapid cooling. Two is that it contains other things beyond SiO2. And then three is we end up with that random arrangement of atoms. So I want us now to talk about oxides. So this slide is titled The Composition of Glasses. And basically what this means is that glasses can be composed of lots of different oxides that can affect the properties. And we break these into 4 categories here. The first category is glass forming oxides. These are also known as glass network or acidic oxides. And they have a generic formula, which would be RO2, where R is just some sort of metal ion, right? Or R2O3, and so examples would be SiO2, right? The other one would be B2O3, which is a boron there. So those are kind of the basis of our oxides. So these tend to be the major structural component. Then the second type are the fluxing oxides. And these are things like that have the formula RO or R2O. They would be like calcium oxide or sodium oxide. The third type are stabilizing oxides. And these would be things like, it would have the formula R2O3, aluminum oxide, right? Boron oxide. And 4, they can be opaquifying oxides. And these would be things like RO2, which would be things like titanium dioxide, tin oxide, zirconium dioxide. And we're going to talk about each of these categories on the next few slides. So the first one I want to talk about are glass forming or acidic oxides. These are the main ingredient in glass. Right? Now, when we talk about the main ingredient in glass, that is SiO2. It forms a tetrahedral structure with a silicon atom in the center, surrounded by 4 oxygen atoms. Okay. So what happens is, and so this is what it looks like. This is called tetrahedral because as you see, it kind of forms a pyramid and it has 4 faces. So there's one face here, one face here, there's a face in the back and a face on the bottom. And that's where the tetra comes from with the 4. This ends up with a formula where it's an ion. It's SiO4 with a -2 charge. This is called the silicate ion. This is a polyatomic ion. There can also be other glasses that are main ingredients. So on the previous slide, we mentioned B2O3. When we talk about this, the one that we talk about most often is, and you'll hear most often, is a borosilicate glass. And that's a mixture of SiO2 and B2O3. And those are the 2 big main components. Okay. Now, these form the glass network. So when we talk about a glass network, what we're talking about here is those SiO4 2- units are linked in a 3D network by bridging oxygen atoms. And so I want you to look over here, and you can see this here, where the black spheres here are Si, the blue spheres are O2-. And so this is the network that they have. Notice it's just really random. But I also want you to notice that we have these other ions that are incorporated. In this case, it's sodium. So when the SiO2 units are linked, they form pockets. So we have these pockets that are present, which can encapsulate cations in order to maintain neutral charges. And it's important to remember this is a disordered array. Now, our second type of oxide are fluxing oxides. And so I want us to define flux really quick. Flux is just a substance added to glass to lower the melting point, and I'm going to abbreviate that as MP, and modify properties. Right? So these are used to lower the melting point of silica. They also are used to lower the viscosity of molten glass. So viscosity is how quickly something flows, or how slowly something flows. And so they're going to lower that. One of the more common fluxing oxides are alkali oxides. These are things like Na2O, which is a lot of times called soda. If you've heard of soda glass, you've got K2O, which is potassa. You've got lithium oxide, which is sometimes called lithia, right? And so specifically, one of the things that happens here is with sodium here, sodium oxide reacts with the silica, and when it does this, it breaks up the silicon network structure. And that's what causes it to act as a flux to melt the glass, is it breaking up that silicon network structure. Other fluxes are alkaline earth oxides. These are like calcium oxide, which is called calcia, manganese or magnesium oxide, which is called magnesia. Right. And every so often you get some others, lead oxide. So if you've heard of lead glass, that's what a lot of times is used as a flux, or zinc oxide. And so maybe the burning question in your heart is, well, where do all of these fluxes come from, right? Where do we find the soda and the potassium and the lithium to mix in with our silica dioxide? Well, the sources of fluxing oxides are aluminosilicate rocks and minerals that are called feldspars. And so they're those sources of the fluxing oxides. And we have specific feldspars. So we have soda feldspars. And I have a picture there for you to look at what feldspars look like. And they have a pretty complex formula where it's Na2O. And then there's a dot, which is not a times, but I'm going to talk about that in a second. Times 6, it's not a times, SiO2. So what this says is these are all form a long-range structure. There's one sodium oxide unit per one aluminum oxide unit per 6 SiO2. And so that's what that dot says to us. You can also have potash feldspars. These are K2O, Al2O3, 6SiO2. That's where the potash there is potassium, and so you can see the potassium is the base of that. Then we can have calcium feldspars. And that's calcium oxide is the base, still with alumina, which is Al2O3, and then 2SiO2. Okay, so the feldspars, which are shown right here, are those sources of our fluxing oxides. Now, another fluxing oxide or source fluxing oxide that we can have is nepheline syenite. This is just another fluxing agent. It's a rock composed of a silicate mineral called orthoclase, which is potassium aluminum Si3O8 feldspar. So it's the orthoclase feldspar. It has a granite-like appearance, and so I've got a picture of it here. With little or no quartz content. So as opposed to the ones on the previous slide that all had silica dioxide incorporated into them in some way, this one does not. And so it's very frequently used as a flux to lower the melting temperature of glass and ceramic. And so what that does is it promotes faster melting, right? And therefore fuel savings, right? So you don't have to use as much fuel to get it to melt, and it melts faster. So fuel costs money, and so this particular flux saves you both time and money if you're using it with your glass. So what do I mean by it lowers the melting point? Well, the melting point of just a potash feldspar is 1686 degrees Celsius. Okay. And so if you look on the graph here, this is our potash feldspar. There is the melting point. Then if you look on the other side, we've got the melting point of silica, and that is 1723. Okay. And so if we look over here, this is 1723, and that's 100% silica. Well, if you mix those two together, what you're going to find is that now their melting point is 990. This is called the eutectic point, and that is just the melting point of a mixture. And notice that melting point is lower than the individual components. Right? So when we mix the potash and feldspar in a 50-50 ratio here, then what we see is it's low, it's like 990. If we increase one or the other, we'll see that it'll gradually creep back up again. But if we have that mixture, it'll be right there kind of at its lowest point. Now, the third type of oxides are stabilizing or adhesive oxides. These are used to control viscosity, inhibit the flow of molten glass, and they also slow down crystal formation. They lower the thermal expansion of glass. And that helps make it resistant to cracking. Under changing temperatures. And examples of this, we talked about it, was R2O3. Those would be things like aluminum oxide, right? And then B2O3, all right, still that boron oxide. And the last oxide that we're going to talk about are opacifying oxides. These are compounds with high refractive indexes. And they're added to make the glass opaque. Right? So tin oxide's refractive index is 2.04. Titanium oxide is what's used more frequently, and that's 2.55 to 2.75. This is apparent in things like milk glass. My grandmother used to collect milk glass, and so we had all of this particular glass that was all around her house. And that is glass that has been mixed in with this titanium dioxide to give it this opaque white appearance here.